Hello, everybody. Thank you for joining me again on another episode of Physics World with Marcos Mason. Today's problem, we are going to be finding the electric field at the center of this ring. And the ring is, of course, one coil in a loop of wire. And we have the information that's been given to us that 5 amps is how much current is running through the wire. And the diameter of the circle was given to us, which is 2 centimeters, so as we can see the radius is going to be 0.01 meters. The next thing that we want to do is figure out what exactly we're solving, and as you can see the way that I've drawn it, it becomes apparent that what we're really dealing with is the superposition of 2 generated magnetic fields. And for superposition, all we really need to do is add them together. So first, to find out if we're adding or subtracting, as they're kind of the same thing but very different, we want to figure out which direction the magnetic field is pointing for each of the components of our problem. So for that, you can use the right hand rule, pointing your thumb in the direction of the current, which works if you imagine that being the top of the circle as well, and then curling your fingers around. And you curl them around, and we can see that it's going into the page. The way that I personally like to imagine the direction of the magnetic field is to picture that I am staring at the current. So I'd be staring this direction as the current is coming toward me. That also still works for the top of the circle. I just pick the top, and I can picture that I'm staring at the current at the top of the circle as it passes. And staring at the current, the magnetic field always has a counterclockwise direction. So we would still arrive at the same conclusion that the magnetic field is pointing into the page. Since they are both contributing magnetic fields in the same direction, we really just have to add the two. So we have the total magnetic field, it's the magnetic field of one plus the magnetic field of the other. And as you can see here, I've broken it down into the components to make it easier. I've separated them. So our magnetic field 1 is going to be at the center of this ring, which we know from our toolbox of equations is mu naught I over 2r. And in the line, it's going to be, the magnetic field 2 is mu naught I over 2 pi d. In this case, we also know that that's the same thing as saying mu naught I over 2 pi r. So down here, I have added them together for ease. If you need to know where the equations came from, Dr. Bensky has an excellent video deriving the equations that are here, but thankfully for me, that is not this video. So we have the magnetic field total is mu naught I over 2r plus mu naught I over 2 pi r. We can rearrange this by the distributive property, and we can enumerate mu naught for ease of calculation, which I like to do these things because it tends to mean I have to enter less into my calculator later. And so we have this equation. 4 pi times 10 to the minus 7 times I all over 2r times 1 plus 1 over pi. And 1 plus 1 over pi, of course, is really the same thing as saying pi plus 1 over pi. Now that I've rearranged it this way, you can see that we can cross out the pi's on the top and the bottom, one from the mu naught and one from our distributive property. And we can reduce the 4 in the numerator because of the 2, so that we just have a 2 times 10 to the 5th times 5 all over 0.01, and this, of course, multiplied by pi plus 1. So that gives us this. And 10 times 10 to the minus 7 is really just 10 to the minus 6, and 0.01 is, of course, 10 to the minus 2. And when I've rearranged it this way, you can see that due to rules of dividing exponents, what we really just have left is 10 to the minus 4. And pi plus 1 is easy enough. We all know the first few digits of pi. And so we're left with the answer without having to punch anything into the calculator of 4.14 times 10 to the minus 4 Tesla. And so now that we've So you can see that the way that we would solve a problem like this is, of course, we just break it down into the different components. We need to figure out which direction they're pointing in, so we know if they're adding or subtracting. And then we can simply plug them all into one equation to find the total magnetic field. And with some rearrangement, that doesn't necessarily even require a calculator. Thank you very much for joining me, and I guess I won't be talking to you again as this is the last physics video, but I hope you have a great year. Bye. Good night.